Now that we ran through the key concepts of AI, let's look briefly at what AI can actually do for nature and climate. Okay? While AI certainly opens new avenues for innovation in the context of climate and nature, it's important to emphasize that these are multifaceted problems. Success will require a combination of capabilities as well as diverse expertise and domain knowledge. It's unlikely that transformative change will come from one solution, one model, one tool, or a technique, but rather through a combination of them. There is vast potential in combining AI's capabilities with expertise and knowledge from diverse domains to create new high impact opportunities for solutions. The most promising of these capabilities include high volume data analysis. AI's capability to process and interpret vast quantities and varieties of data is unprecedented. We already know that, and they are already being used as such by combining various types of images from cameras, drones, unmanned aerial vehicles, and remote sensing satellite imagery, sensory data and Internet of Things, network connectivity, bioacoustic data, and more. Can also be used to identify and interpret complex relationships in large data sets and more efficiently compress and share large amounts of data. So you can hardly go wrong with AI as it stands now, and then we'll see what are the issues. Monitoring, of course, AI is being used to now reduce the time and labor in monitoring processes such as massive data sets coming from satellites or real-time energy consumptions that is being tracked, and also these can be streamlined and automated by AI. AI can classify, segment, or analyze such data from images to time series information much more quickly and accurately, allowing for faster, better informed decision making. Okay, that's obvious. Optimization is always important when you have money on the line. Given its speed, accuracy, and low computing requirements compared to other computational techniques, once trained, AI is already invaluable to climate solutions. Right? They can contribute to a reduction in emissions, other environmental benefits, and we'll see some examples of where they are being already applied, such as monitoring impacts, predicting climate at various weather and climate, as well as improved predictions of cyclones, applications for agriculture, water, biodiversity, industries, and cement, steel, for example. Predictive modeling and forecasting, as I mentioned already, trained on massive amounts of data using past and current conditions as inputs, AI can more accurately and more efficiently predict future behavior or conditions. The question is how far into the future you can go. If you think of AI crudely as some sort of an interpolation and then extrapolation, what is the role of physics in guiding the future projections or predictions? So there are physics-based models and there are data-driven models and so on that you can read about more. So applying this capacity to assess and optimize crop yields, energy demand, transportation mobility, carbon sinks, weather or climate projections, etc., can lead to both savings and emissions reductions, which is the goal of handling climate change, managing climate change, and heading towards sustainability. And we'll see some examples briefly. Digital twins, we already mentioned what they are. Obviously, they are now being mentioned more and more. Are they actually being implemented? It's not so easy in reality because we will need a tremendous amount of data to do it. But nonetheless, creating digital counterparts of terrestrial, aquatic, industrial, or urban environments, for example, enables experimentation or counterfactuals without the risk of harm to the environment, while still accelerating solution-oriented designs, informing implementation strategies, and supporting efficient decision-making for climate mitigation, adaptation, and nature-based solutions. Okay, so counterfactual world here is basically to see if we are doing climate change, where we have gone, and if we didn't do climate change, where we would have gone. So that's the counterfactual world where we didn't have any impact. These are very important and can only be done with models, right? You cannot go back and change nature and say from the Industrial Revolution, if we didn't emit CO2, what would have happened? in the model we can do that. Acceleration of discovery, of course, protein structures to everything, but AI can play here a pivotal role in uncovering novel solutions, leveraging its unique capability to process vast amounts of data across various disciplines, as well as its ability to learn nonlinear and intricate relationships within the data that is given to it. I won't read more about it. How recent AI can be used for climate and nature. Many current and emerging AI models and applications have the potential to create high impact opportunities in the context of climate and nature, even if they were not originally developed for that purpose. For example, advances in unstructured data analysis and prediction, edge computing, and multimodal AI could all lead to the acceleration of solutions. Beyond the key AI capabilities such as high volume data analysis, monitoring, optimization, digital twins, predictive modeling, and acceleration of discoveries that we went through, we have also seen important recent developments in AI that could present important tools for climate and nature applications, and we'll see some applications that are already underway. This is a nice long section. I should read it, so maybe let's just go ahead and do it. Graph structure data analysis and prediction, GraphCast I think it's called, which is what Google is doing, but make sure that I'm saying the right thing. Many datasets are not organized as sequences or over spatially regular grids. It could be Lagrangian data, for example, an aircraft collecting or a ship collecting or a drone and so on. Graph neural networks are powerful tools that can model the intricate relationships of graph-like structured data. GNNs are well suited for many climate and natural applications because of their capacity to handle complex structured data such as those present in hydrological networks, sparse weather or pollution station data, and at the multi-scale nature of turbulent fluids found in the atmosphere, cyclones, and then scale down to the prediction level that matter for actual accurate predictions. By incorporating information from neighboring nodes and edges within the graph structure, GNNs can produce a generic model to improve the prediction of complex spatiotemporal behaviors across scales. If you don't understand the details, don't worry, just kind of listen and say, well, they can do all these things. Edge computing, again, we talked about it. The edge computing ecosystem allows computations to be performed in close proximity to the data collection points, so localization of the analysis, i.e. at the edge of such at the edge such as near an observing camera, limiting the needs for substantial internet bandwidth. So enough computing power and energy to do it locally and make decisions. That's the critical part. This approach leverages IoT to address issues of data collection, communication at scale, and real-time decision making. Edge computing technologies help expedite the development of data infrastructure by enabling the wider distribution of edge devices. In-house monitoring, smart grids, and real-time analysis of energy consumption are all current edge computing applications. Edge computing has significant transformative potential in real-time monitoring, which is critical to evaluating developments in climate and nature. In the field of bioacoustics, for example, audio data collected from ocean and species monitoring sensors can be processed in remote and challenging environments. Edge computing enables efficient and scalable solutions that are instrumental in advancing bioacoustics monitoring efforts. We'll see an example of identifying species, which is just one of the applications. People are collecting bird sounds and figuring out that birds can talk, elephants call each other by names, whales have individual calls, or they also have conversations, and so on and so forth. The accumulated biodiversity data can then be used to establish foundational models in climate and environmental studies, and we defined foundational model before. Multimodal, we defined foundation models. Foundational models can be thought of as seminal models also. Multimodal AI, multimodal AI. In climate, we always have multi-model ensembles and so on. Here, multimodal AI is designed to analyze and amalgamate data from multiple sources with varying levels of coverage, resolution, and quality. These techniques enable in-depth analysis of intricate relationships and foster a comprehensive understanding of system dynamics and shifts. In the climate and nature domain, multimodal requirements are the norm. Environmental data are required by various sensors with varying coverage, resolution, and quality. Multimodal AI can optimally integrate these diverse data streams and synthesize climate and nature data from multiple sources such as in situ observations, drones, and various remote sensing platforms, thereby facilitating monitoring of land cover, land use, vegetation health, and environmental changes across temporal and spatial scales. Data from sources like acoustic sensors, camera traps, and GPS tracking devices can also be optimally leveraged through multimodal AI and used to analyze species distributions, monitor wildlife populations, and assess biodiversity metrics. So combined with digital twins, you can imagine how you can create protected areas and conservation efforts for species or ecosystems and so on. So let's then come back and look at the considerations for AI development. You can already see some keywords like equity, justice, governance, safety, security, equal opportunities, and so on. So we will then jump to current applications of AI and look at some specific examples of what is already being done. This is only 11 minutes, so maybe I will just read a bit more. Sorry to do this on the fly. So before moving to the next chapter, let's just do that here. Bringing up the laser pointer. What are the considerations for AI development for nature and climate then? Innovation and economic growth that have delivered remarkable gains in human well-being and wealth since the Industrial Revolution have also had negative consequences, including widespread destruction of the natural world and deepening inequality. The very engines of growth, such as energy sector, industry, agriculture, forestry, etc., are the primary drivers of climate change. In turn, the compounding impacts of climate change and its drivers, including land and sea use change and exploitation of natural resources, along with pollution and invasive species, are leading to the widespread degradation of nature. And with the rapid advances in both development and deployment of AI, its potential for negative social and environmental consequences, often in ways not yet understood, is raising concerns for funders, developers, policymakers, and practitioners alike. I have a podcast on how AI itself has to become sustainable, because always so much computing is involved, so much energy demand, water demand is involved, that it itself is a big part of climate change unless we take care of that and make AI itself sustainable. So AI for sustainability and sustainable AI for sustainability. Okay, so again, as I said already, equity, justice, governance, safety and security, equal opportunities, etc. are key for consideration when developing AI. And if these are happening at international levels, then you can imagine how difficult this is going to get. Already we are facing negotiations under UNFCCC. COP29 just concluded with lots of unhappy people, but some progress is being made, and then we always worry about whether the progress is fast enough and so on. So sustainability is again important. It's impossible to address the potential of AI without also scrutinizing its energy consumption, as I mentioned. The computing power required to process and analyze massive amounts of data necessitates significant energy consumption and water resources for cooling of hardware, and all this data is stored on clouds. Clouds are massive energy hogs and water hogs, and every time you have something that is moving and doing edge computing, it's requiring some energy from somewhere, or an autonomous vehicle, drone, self-driving cars. They're all constantly collecting data and doing edge computing and making decisions in near real time, and that's all energy and emissions and water. So all that is AI related as well. So then we'll come back and look at current applications of AI We'll look at some applications in nature, food and agriculture, power sector, cities and built environment, greenhouse gas emissions and climate impacts. I will be very brief. There is a lot of text. I will just use the graphics to show the initiatives and efforts that can be by companies like Google or universities like Stanford or other players, governments, organizations, scientific organizations, and so on and so forth. Okay, so see you in the next topic, which is on the current applications of AI. Okay.